You have 60 seconds before your blood boils, your bones are already breaking, and the radiation, it's rewriting your DNA as we speak. Welcome to your first day on Mars, and you haven't even left the spacecraft yet. Your first year on Mars would fundamentally test everything that makes you human. And here is a question. If you could only bring 3 personal items to Mars for your first year, what would they be? Comment down below. I will pin the most creative answer. Now let's begin. Let's paint a picture of what you're actually dealing with. Mars isn't just another planet. It's a frozen desert world where the average temperature sits at around -63 degrees Celsius. That's colder than Antarctica on its worst day. The atmosphere? It's 95% carbon dioxide, and it's so thin that it's less than 1% of Earth's atmospheric pressure. Standing on Mars without a spacesuit would be like standing in a near-perfect vacuum. Your blood would literally start to boil. But here's what makes Mars so fascinating to scientists and so critical to humanity's future. This rusty world isn't completely hostile to life. Deep beneath that frozen surface, there might be liquid water. Ancient riverbeds carve across the landscape like scars from a time when Mars had flowing rivers and maybe even oceans. NASA's Perseverance rover is right now, as we speak, drilling into rocks that formed in what used to be a massive lake, searching for signs that life once existed there. Think about that for a moment. You might be stepping onto a world where life once thrived billions of years ago. The latest data from NASA's MAVEN spacecraft, which has been orbiting Mars since 2014, revealed something remarkable. Mars once had a thick atmosphere and a magnetic field, just like Earth. But around 3.5 billion years ago, something catastrophic happened. The planet's magnetic field collapsed, and solar wind stripped away most of the atmosphere. What remained was a cold, radiation-soaked world. Yet despite all of this, Mars is still the most Earth-like planet in our solar system. Its day is nearly identical to ours at 24 hours and 37 minutes. It has seasons, polar ice caps made of water, and frozen carbon dioxide, and massive volcanoes that dwarf anything on Earth. Olympus Mons, the tallest volcano on Mars, rises 22 kilometers above the surrounding plains. That's nearly 2.5 times taller than Mount Everest. Imagine standing at the base of that mountain, looking up at a peak that pierces through most of the thin Martian atmosphere. These geological wonders tell us that Mars was once an incredibly active world, and understanding what happened to it might help us understand Earth's own future. So why go there at all? Why would you subject yourself to a year of unimaginable hardship on a frozen, airless rock millions of kilometers from home? Because you would be part of the greatest adventure in human history. You would be answering questions that humanity has asked since we first looked up at the night sky. Are we alone? Can life exist beyond Earth? Can humans become a multi-planetary species? Your first year on Mars would make you a pioneer in the truest sense of the word. Every challenge you face, every problem you solve, every data point you collect would pave the way for future generations. You'd be the living proof that humanity can survive beyond our home planet. You are made of stardust, forged in the hearts of ancient stars, and your journey to Mars would be the continuation of a cosmic story that began 13.8 billion years ago with the Big Bang. But let's be honest about what you're signing up for. The NASA Chapiar missions, which simulated Mars conditions right here on Earth with volunteers living in a 3D printed habitat for 378 days, revealed psychological and physical challenges that no amount of training can fully prepare you for. The crew experienced isolation, communication delays with mission control, equipment failures they had to fix themselves, and the monotony of eating the same limited food options day after day. And that was in a simulation with blue skies visible outside and the knowledge that they could leave if a real emergency happened. Now imagine that same experience, but you can't leave, ever. There are no blue skies, just rust-colored dust, and a black sky even during the day. The nearest help is millions of kilometers away and takes anywhere from 4 to 24 minutes for a radio signal to reach, depending on where Earth and Mars are in their orbits. You can't call home and have a conversation. You send a message and wait. You hear their response and wait. Every decision that needs to be made quickly falls entirely on you and your crew. If you're finding this fascinating, make sure you hit that subscribe button and give this video a thumbs up. Your support helps this channel grow and allows me to bring you more content about the wonders and mysteries of space exploration. Let me tell you about radiation, because this is where your first year on Mars becomes genuinely terrifying. On Earth, you're protected by two invisible shields that you probably never think about. First, there's Earth's magnetic field generated by the churning molten iron in our planet's core. This magnetosphere extends thousands of kilometers into space, deflecting most of the deadly charged particles streaming from the Sun. Second, there's our thick atmosphere, which absorbs and scatters the radiation that does make it through. Mars has neither of these protections. Its magnetic field died billions of years ago, and its atmosphere is less than 1% as thick as Earth's. This means you're exposed to two types of radiation that would fundamentally change your biology over time. First, there's solar radiation from our Sun, especially during solar flares when massive amounts of charged particles come racing toward the planet. Second, and far more dangerous, there's galactic cosmic radiation. These are high-energy particles that have been traveling through space for millions of years, accelerated by distant supernova explosions. They're so energetic that they can pass right through your spacecraft, your habitat, and your body, smashing into your DNA and damaging it at a cellular level. Research published in the journal PLOS One analyzed the radiation exposure astronauts would face during a mission to Mars. The findings are sobering. During a round trip to Mars, lasting approximately 2.5 to 3 years, including surface time, astronauts could receive a radiation dose that increases their lifetime cancer risk by 5 to 10%. But here's the truly concerning part. That's just the central estimate. The upper confidence interval suggests the risk could be even higher, potentially reaching 20% for certain individuals. Let me put that in perspective for you. NASA's current safety standards limit astronaut radiation exposure to a 3% increase in lifetime cancer risk. A mission to Mars would blow past that limit immediately. You would absorb more radiation in 1 year on Mars than a nuclear power plant worker receives in their entire career on Earth. And we're not just talking about cancer risk here. Recent studies have identified another insidious danger: cardiovascular disease. When high-energy cosmic rays pass through your body, they don't just potentially cause cancer, they damage the cells lining your blood vessels, accelerate atherosclerosis, and increase your risk of heart attacks and strokes years or even decades after your mission ends. Research on atomic bomb survivors and radiation therapy patients has shown this connection clearly. But cosmic radiation is different from the radiation we understand from Earth-based sources. It's far more energetic, and we're only beginning to understand its full biological effects. Your brain is particularly vulnerable. Studies on mice exposed to radiation similar to galactic cosmic rays showed concerning changes in brain function. The radiation damaged neural pathways involved in memory, learning, and decision-making. Imagine trying to make critical life or death decisions while your cognitive abilities are slowly degrading. Even more troubling, some researchers worry about increased anxiety, impaired memory formation, and difficulty with executive function. You might start forgetting procedures you've trained on for years. You might struggle to solve problems that should be straightforward. And here's something that keeps mission planners awake at night. we can't fully shield you from this radiation. You might think building thicker walls would solve the problem, but cosmic rays are so energetic that when they hit shielding material, they can actually create secondary radiation through a process called spallation. Heavy shielding can sometimes make the problem worse. The MOXIE experiment on NASA's Perseverance rover, which successfully produced oxygen from Martian atmosphere, completed its mission in September 2024. This technology will be crucial because one solution to radiation involves covering your habitat with several meters of Martian soil called regolith. But that requires enormous infrastructure you won't have during your first year. You might spend most of your time in a small, heavily shielded storm shelter, only coming out when absolutely necessary. During solar storms, which can increase radiation levels by factors of 10 or more within hours, you'd need to retreat to this shelter and wait it out, potentially for days. Solar storms are unpredictable. The largest one on record, called the Carrington event, happened in 1859. If a storm of that magnitude hit Mars while you were outside conducting research, even your spacesuit wouldn't provide adequate protection. You'd need to get back to your shelter within minutes or risk acute radiation sickness. Now, let's talk about something equally critical but less obvious: your muscles and bones. You've probably heard that astronauts lose bone density and muscle mass in space, but do you understand why this matters so much for Mars? Earth's gravity is constantly working against you, forcing your bones to stay strong and your muscles to work just to keep you upright. Remove that stress and your body starts to think, why am I maintaining all this expensive bone and muscle tissue if I don't need it? On the International Space Station, astronauts lose about 1 to 2% of their bone density per month, despite exercising for 2.5 hours every single day. Mars has only 38% of Earth's gravity, which means the problem is less severe than in zero gravity, but it's still significant. During your 6 to 9 month journey to Mars, you'd be in zero gravity, arriving at the red planet with significantly weakened bones and muscles. Then you'd need to immediately start working in Martian gravity, which is enough to pull you down but not enough to maintain your bone and muscle mass long term. Think about what this means practically. You're wearing a spacesuit that masses around 55 kilograms on Earth, but would only weigh about 21 kilograms on Mars. That sounds manageable until you realize that mass and inertia don't change with gravity. The suit is still just as hard to move around in, still just as bulky and restrictive. You're trying to do complex repairs, scientific experiments, and construction work while essentially disabled by bone loss and muscle atrophy. Simple tasks become exhausting, your coordination suffers, your risk of injury skyrockets. And here's the terrifying part. If something goes catastrophically wrong and you need to return to Earth, could your body even survive the journey back? After a year on Mars, your bones would be significantly weakened. The 9-month journey home in zero gravity would weaken them further. When you finally reach Earth, could you even stand up under full gravity? Would your brittle bones shatter under stresses they use to handle effortlessly? Speaking of which, if you want to understand just how terrifying Mars colonization truly is, I've created an entire video exploring the darker realities that most people don't talk about. It's called Mars Colonization is More Terrifying Than You Think, and it dives deep into challenges that would make your first year look easy by comparison. The link is in the description and on the card above. But let's get back to your first year. We need to talk about isolation, because this might be the challenge that breaks you. Human beings evolved as social creatures. Your brain is literally wired to need social interaction. Studies of people in extreme isolation, from prisoners in solitary confinement to researchers wintering over in Antarctica, consistently show that isolation does something to the human mind. You start to change in ways you can't fully control. The Mars 500 simulation conducted by Russia and the European Space Agency locked 6 volunteers in a sealed habitat for 520 days to simulate a Mars mission. The results were eye-opening. One crew member showed symptoms of depression 93% of mission weeks, reaching mild to moderate levels more than 10% of the time. Another developed chronic insomnia that lasted the entire mission, leading to sleep deprivation, exhaustion, and impaired cognitive function. Two crew members became so stressed they accounted for 85% of all perceived conflicts during the entire mission. Now imagine that same psychological pressure, but amplified. In the Mars 500 simulation, the crew knew it was temporary. They knew that outside their sealed habitat, Earth was right there with its blue skies, forests, oceans, and 7 billion people. You won't have that comfort. When you look outside your habitat window on Mars, you'll see an alien landscape that hasn't changed in millions of years. The same rust-colored rocks, the same pink sky during dust storms, the same absolute absence of anything living. No birds, no insects, no plants, no movement except dust blown by thin winds. Your crew will probably consist of 4 to 6 people. These are the only human beings you'll interact with face-to-face for an entire year. You can't take a walk to clear your head. You can't visit a friend in another city. You can't escape to a movie theater or a restaurant or a park. You're trapped in a habitat that might be only 150 to 200 square meters in total living space. That's smaller than most houses, and you're sharing it with several other people who are dealing with their own stress, fear, and psychological challenges. Communication with Earth involves delays ranging from 4 to 24 minutes one way, depending on the planet's positions. This means every conversation is asynchronous. You send a message, you wait, you receive a response, you reply, you wait again. You can't have a real-time conversation with anyone you love. You can't call your parents when you're feeling homesick. You can't video chat with friends when you need emotional support. Every interaction is delayed, sterile, disconnected. The psychological literature calls this the third quarter phenomenon. It's been observed in Antarctic expeditions, submarine deployments, and long-duration space missions. During the first quarter of your mission, excitement and novelty carry you through. You're on Mars, you're making history, but that wears off. The second quarter involves settling into routines and accepting the reality of your situation. The third quarter is when things get dangerous. The novelty is completely gone. The end feels impossibly far away. Boredom, depression, and interpersonal conflicts spike dramatically. People become irritable, withdrawn, or hostile. NASA's CHAPIA simulations specifically studied this. Crew members reported that conflicts with mission control happened 5 times more often than conflicts among crew members themselves. Why? Because mission control represents the outside world that has no idea what you're actually going through. They're sitting in comfortable offices on Earth, eating whatever food they want, seeing their families every night, and they're telling you what to do. The resentment builds. The feeling that nobody understands becomes overwhelming. And here's something that doesn't get discussed enough: guilt. You've left everyone you love behind for this mission. While you're on Mars, continues on Earth without you. Your parents age, your friends move on, relationships change, people get married, have children, experience triumphs and tragedies, and you're not there. You're watching humanity's story unfold from a distance, always an observer, never a participant. The guilt of missing important moments combined with the knowledge that you chose this can be psychologically crushing. Your circadian rhythm, the internal clock that regulates your sleep-wake cycle, will also be disrupted. A Martian day, called a sol, is 24 hours and 37 minutes long. That sounds trivial, but studies show that even this small difference can cause chronic sleep disruption. Your body wants to operate on a 24-hour cycle because that's what billions of years of evolution on Earth programmed into your DNA. Forcing it to adjust to a slightly longer day creates persistent misalignment. In the Mars 500 simulation, crew members showed significantly altered sleep-wake patterns that persisted throughout the entire mission. Poor sleep doesn't just make you tired, it impairs your immune system, making you more susceptible to illness. It degrades cognitive function, increasing the likelihood of dangerous mistakes. It worsens mood disorders like depression and anxiety. And remember, you're already dealing with radiation exposure, muscle and bone loss, isolation, and the constant stress of knowing that any serious malfunction could kill you. Add chronic sleep deprivation to that list, and you've got a recipe for disaster. Let's talk about something more immediate: breathing. On Earth, you walk outside and breathe without thinking about it. The atmosphere is 21% oxygen, and it's at a pressure your body is perfectly adapted to. On Mars, stepping outside without a spacesuit means instant death. The atmospheric pressure is so low that the moisture in your lungs would immediately start to boil. Within 15 seconds, you'd lose consciousness. Within 1 to 2 minutes, you'd be dead. This means you're dependent on technology for every single breath. Your habitat needs to maintain Earth-like atmospheric pressure and oxygen levels constantly. Your spacesuit needs to do the same when you venture outside. If either system fails, you have minutes or seconds to fix the problem before you die. The psychological weight of this constant dependence on life support systems is difficult to overstate. You can never relax completely. There's always a part of your mind monitoring the systems, listening for alarms, checking readouts. NASA's MOXIE experiment on the Perseverance rover proved that we can produce oxygen from the Martian atmosphere. MOXIE successfully converted carbon dioxide into oxygen 16 times before its mission concluded in September 2024. Producing oxygen at twice its required rate with 0 failures. This is incredible news for future Mars missions, but here's the catch. MOXIE is a small demonstration unit. Scaling up this technology to support human life requires building industrial-scale equipment, and you probably won't have that during your first year. Instead, you'll likely depend on oxygen brought from Earth or produced through chemical processes using supplies you brought with you. You'll need to carefully ration and recycle everything. The water you drink today becomes the water you wash with tomorrow, and the water you use to grow plants the day after that. Your urine will be filtered and purified back into drinking water, just like on the International Space Station. Every breath you exhale releases carbon dioxide that needs to be scrubbed from the air and either vented outside or converted back into oxygen. This brings us to food, and this is where your first year becomes a test of culinary monotony. You're not going to have fresh fruit. You're not going to have fresh vegetables unless you can grow them yourself, and that's an enormous challenge we'll discuss in a moment. Most of your food will be freeze-dried, vacuum-sealed, or otherwise preserved for the multi-year journey from Earth. Think of military MREs, meals ready to eat, but even more limited in variety. Studies of long-duration missions consistently show that food becomes a major psychological issue. The monotony of eating the same limited selection of meals week after week, month after month, wears people down. Food isn't just fuel, it's comfort, it's culture, it's one of the few pleasures available to you. When that becomes boring and unappetizing, morale plummets. NASA has spent decades trying to improve space food, but there are hard limits imposed by mass restrictions, preservation requirements, and the lack of refrigeration. You might attempt to grow fresh food in a small greenhouse, and this could be one of the most important activities for both your physical and mental health. The act of nurturing living plants, watching them grow, and harvesting fresh food provides psychological benefits that go far beyond nutrition. It gives you a sense of purpose, a connection to life, and a break from the sterile, mechanical environment of your habitat. But growing food on Mars is extraordinarily difficult. Martian soil, or regolith, isn't really soil at all. It's more like volcanic ash mixed with toxic compounds. One of the biggest problems is perchlorate, a chemical compound that exists in Martian regolith at concentrations around 0.5% to 1%. Perchlorates are toxic to humans and interfere with thyroid function. If you tried to grow plants directly in Martian regolith and then ate those plants, you could poison yourself. The soil needs to be extensively washed and treated before it's safe to use, and even then, you'd probably need to supplement it with nutrients and organic matter brought from Earth or produced from your own waste. Water is another massive challenge. We know Mars has water ice beneath the surface and at the polar regions, but accessing it requires energy-intensive processes. You'd need to drill or excavate the ice, melt it, purify it, and then use it for both life support and agriculture. Every liter of water you use for growing plants is water that could have been used for drinking, hygiene, or oxygen production. The trade-offs are constant and unforgiving. Light is also problematic. Mars receives only about 43% as much sunlight as Earth because it's farther from the Sun. During dust storms, which can last weeks or even months and sometimes envelope the entire planet, surface light levels can drop to a small fraction of normal. The massive dust storm in 2018 was so severe that it blocked out the Sun completely in some areas, killing NASA's Opportunity rover after nearly 15 years of operation. If you're depending on solar panels for power and on sunlight for growing food, a global dust storm could be catastrophic. You'd likely need to grow plants indoors under artificial LED lighting, which requires enormous amounts of electrical power. Every watt of electricity you generate needs to be carefully allocated between life support, heating, scientific equipment, communications, and agriculture. There's never enough power to do everything you want to do. You're constantly making difficult choices about priorities. Speaking of electricity, let's talk about power generation, because this is fundamental to your survival. On Earth, when your power goes out, it's an inconvenience. On Mars, it's a death sentence if it lasts too long. You need power for oxygen generation, carbon dioxide scrubbing, water recycling, heating, communications, lighting, food production, and charging the batteries in your spacesuits and rovers. Without power, you die. It's that simple. Solar panels seem like the obvious choice. Mars gets plenty of sunlight most of the time, and photovoltaic technology is well understood. But Martian solar panels face unique challenges. Dust accumulation is a constant problem. The fine, electrostatically charged Martian dust clings to everything, and there's no rain to wash it off. NASA's rovers have sometimes benefited from cleaning events where dust devils, small whirlwinds, happen to pass over the solar panels and blow the dust off. But you can't count on dust devils. You'd need regular manual cleaning, which means EVAs, extravehicular activities, which expose you to radiation and use up consumables from your spacesuit. Then there are the dust storms. During a major dust storm, your solar panels might produce only 10 to 20% of their normal output for weeks. You'd need massive battery banks to store enough energy to survive these periods, and batteries are heavy. Every kilogram of batteries is a kilogram you couldn't use for food, water, spare parts, or scientific equipment. The alternative is nuclear power, specifically a small nuclear reactor or radioisotope thermoelectric generators. NASA's Curiosity and Perseverance rovers use RTGs, which generate heat from the radioactive decay of plutonium-238 and convert that heat into electricity. They're reliable, work day and night regardless of dust storms, and require no maintenance, but they're expensive, politically controversial, and produce relatively small amounts of power. A human mission would need something much larger, like a small fission reactor capable of generating tens of kilowatts continuously. The challenge is that developing, testing, and safely transporting a nuclear reactor to Mars is a massive undertaking. It needs to survive the launch, the journey, and deployment on Mars. It needs to operate reliably for years without maintenance in a harsh environment. Any malfunction could contaminate your habitat area with radioactive material. During your first year, you might be relying on a combination of solar panels and small RTG units, constantly worrying about whether you have enough power to make it through the next dust storm. Temperature regulation is another survival challenge that's easy to underestimate. Mars is cold, really cold. The average temperature is -63 degrees Celsius, but it varies wildly. At the equator, during summer, daytime temperatures might reach a comfortable 20 degrees Celsius. But at night, they can plummet to -73 degrees Celsius. At higher latitudes, or during winter, temperatures can drop below -125 degrees Celsius. Your habitat needs to keep you at a comfortable temperature despite these extremes, and that requires energy. Heating is actually a bigger concern than cooling on Mars. You'd lose heat through conduction to the cold ground, through radiation to the cold sky, and through any imperfections in your habitat's insulation. The thin atmosphere provides almost no insulation itself. Maintaining a comfortable interior temperature of around 20 degrees Celsius requires constant energy input. Here's an interesting paradox. Sometimes you'd need cooling, not heating. Your habitat contains electronic equipment, human bodies, and maybe grow lights, all of which generate waste, heat. On Earth, you'd just open a window or turn on air conditioning. On Mars, you can't open a window because there's no breathable atmosphere outside. Radiating heat into the thin Martian atmosphere is difficult because there aren't enough air molecules to carry the heat away efficiently. You'd need carefully engineered heat exchange systems, and if they fail, your habitat could overheat despite the freezing conditions outside. Now let's discuss something that terrifies mission planners: medical emergencies. On Earth, if you have a serious injury or sudden illness, an ambulance can reach you within minutes and transport you to a hospital with advanced equipment and specialist doctors. On Mars, you are the hospital. Your crew might include someone with medical training, possibly even a doctor, but you won't have an operating room, advanced imaging equipment, or access to specialists. What happens if someone develops appendicitis? On Earth, that's a routine surgery. On Mars, it could be fatal. You might have basic surgical tools and supplies, but performing an appendectomy in a small habitat with limited equipment, no anesthesiologist, and no backup if something goes wrong is terrifying. The person acting as surgeon would be under unimaginable pressure. One mistake, one complication, and a crew member dies. And if that crew member happens to be the person with the most critical skills for mission success, the entire mission could be jeopardized. Dental emergencies are another concern that sounds minor, but could become serious. A severe toothache, an abscess, or a broken tooth can be incapacitating. Dental infections can spread to your bloodstream and become life-threatening. You'd have basic dental supplies and perhaps someone trained in emergency dentistry, but complex procedures would be nearly impossible. Astronauts going to Mars would likely have all their wisdom teeth removed and any potential dental problems addressed before the mission. But problems can still develop. Injuries are almost inevitable. You're working in a hazardous environment, wearing bulky spacesuits, operating complex equipment, and dealing with the effects of reduced gravity on your coordination. A simple fall that would bruise you on Earth could break weakened bones on Mars. A cut that would be minor on Earth becomes a serious infection risk in an environment where your immune system is compromised by radiation exposure, stress, and isolation. And what about psychological emergencies? What if someone becomes severely depressed or suicidal? What if someone develops psychosis or has a complete mental breakdown? These aren't hypothetical concerns. They've happened in extreme isolation environments on Earth. In Antarctica, a doctor once had to perform surgery on himself because he was the only medical person at the station. In another case, a researcher became so depressed during the winter isolation that they required emergency evacuation, which was only possible because they were still on Earth. On Mars, there's no evacuation option. If someone becomes a danger to themselves or others, the crew has to handle it. You might need to sedate them, restrain them, or isolate them, all while trying to maintain mission operations and keep everyone else psychologically stable. The guilt, fear, and trauma of dealing with a crew member in crisis would affect everyone's mental health for the rest of the mission. Let's talk about something more subtle but equally important: the loss of sensory experience. Human beings evolved in an environment rich with sensory input: the smell of rain, the feel of wind on your skin, the sound of birds, the taste of fresh food, the sight of green plants and blue skies. All of these sensory experiences are deeply connected to your psychological well-being, even if you don't consciously think about them. On Mars, your sensory world becomes impoverished. Inside your spacesuit or habitat, you smell recycled air that's been filtered and scrubbed, probably with a slight metallic tang. You don't feel wind or rain. You don't hear natural sounds, only the hum of machinery, ventilation fans, and equipment. When you look outside, you see the same rusty landscape every single day. The sky is either butterscotch-colored or, during dust storms, an oppressive reddish-brown. Even the sun looks different, appearing only about 2/3 the size it does from Earth, because Mars is farther away. This sensory deprivation has psychological effects that are hard to predict. People in sensory deprivation experiments report hallucinations, anxiety, depression, and difficulty thinking clearly. You won't be in complete sensory deprivation, but the monotony and lack of natural sensory richness could slowly erode your mental health in ways that are difficult to measure or address. There's also the issue of smell. On the International Space Station, astronauts report that everything starts to smell stale after a while. Your nose adapts to the constant background smell, but you become acutely aware of any new odors, and in a closed environment, those new odors are often unpleasant. Body odor, food smells, equipment off-gassing, and waste management all contribute to an olfactory environment that's just slightly unpleasant all the time. It seems like a minor issue, but these small, constant irritations accumulate and affect morale. Your sense of time will also become distorted. On Earth, you have natural rhythms that help you track time, the changing seasons, weather variations, social events, holidays, and interactions with a dynamic society. On Mars, every day is essentially the same. You wake up, perform your assigned tasks, eat the same limited food, interact with the same small group of people, and go to sleep. Weeks blend together. Months feel both impossibly long and somehow compressed. Research on time perception in isolation shows that people lose their sense of how much time has passed. Days feel longer because they're monotonous, but when you look back, months seem to have vanished because nothing distinctive happened to create memory markers. This temporal disorientation can be deeply unsettling. You might find yourself wondering, have I really been here for 6 months? It feels like both 6 days and 6 years. The concept of home becomes complicated. Earth is home, but it's unreachable. Your habitat is where you live, but it doesn't feel like home. It feels like a machine you're living inside, a survival shelter. The psychological need for a sense of place, for somewhere that feels safe and comfortable, and yours, goes unfulfilled. Astronauts on the ISS deal with this by personalizing their small crew quarters with photos and mementos, and you'd likely do the same, but the fundamental alienness of your environment would never completely go away. Communication technology will be your lifeline to Earth, but it comes with frustrations that will test your patience daily. The speed of light is finite, and the distance between Earth and Mars varies between about 55 million kilometers at closest approach to over 400 million kilometers at the farthest point. This creates signal delays ranging from about 3 minutes to 24 minutes one way, or 6 to 48 minutes for a complete exchange. Imagine trying to troubleshoot a critical system failure with engineers on Earth. You describe the problem and send the message. You wait 15 minutes. They ask clarifying questions. You wait another 15 minutes to receive their questions. You answer and wait. They suggest a solution. You wait. By the time you receive their suggestion, the situation may have changed completely. Time-critical decisions have to be made without consultation. You and your crew are truly on your own. Video calls with family become surreal experiences. You record a message, talking to a camera, trying to share your experiences and emotions. Then you wait. Eventually, you receive their response, recorded earlier, and you watch them react to things you said half an hour ago. The natural flow of conversation is impossible. You can't react to each other in real time. You can't provide immediate comfort when someone's upset. Every interaction feels stilted, artificial, and emotionally unsatisfying. Social media and news from Earth present another psychological challenge. You'd likely have access to internet content sent in regular data packages, but it would always be delayed and curated. You'd be watching a version of Earth's events that's hours or days old, feeling increasingly disconnected from the rapid flow of human culture and current events. You're simultaneously part of the biggest news story on Earth, the first humans living on Mars, and yet completely removed from participating in the conversation about it. The knowledge that billions of people are watching your mission, analyzing your every move, and debating your decisions adds another layer of pressure. There's no privacy beyond the walls of your habitat, and even there, communications are monitored by mission control. You can't have a bad day without the world potentially knowing about it. You can't make a mistake without it being scrutinized by experts and armchair critics alike. The psychological weight of performing under this level of constant observation is immense. Now let's discuss something that might sound mundane but becomes critically important: hygiene and waste management. On Earth, you shower, use the toilet, wash your hands, and brush your teeth without thinking about where the water comes from or where the waste goes. On Mars, every drop of water is precious, and every bit of waste must be carefully managed. Showers, as you know them, won't exist. Water is too valuable to spray over your body and wash down a drain. Instead, you'd use something more like a sponge bath with minimal water, probably recycling even that water afterward. Your skin and hair would never quite feel clean. ISS astronauts describe feeling perpetually slightly grimy, and you'd experience the same thing, except for a year instead of a few months. Toilet facilities on Mars would be sophisticated but far from comfortable. Everything must be captured, separated, and processed. Solid waste needs to be collected, possibly composted or sterilized and stored. Urine needs to be filtered and purified back into drinking water through a process that, while scientifically sound, is psychologically difficult to accept. Astronauts joke about drinking yesterday's coffee becoming today's coffee again, but the reality of consuming water reclaimed from your own waste takes mental adjustment. The closed-loop life support systems require constant monitoring and maintenance. Filters need to be changed, pumps need to be checked, and chemical processes need to be recharged or replaced. A failure in the water recycling system doesn't just mean you can't shower, it means your water supply is dwindling and you could die of dehydration. The stakes transform every maintenance task from a chore into a life or death responsibility. Laundry presents another problem. Washing clothes requires water and energy, both of which are scarce. On the ISS, astronauts simply don't do laundry. They wear clothes until they're too dirty, then throw them away in cargo ships that burn up in Earth's atmosphere. On Mars, you can't throw anything away because there's nowhere for it to go and no resupply ships arriving regularly. You'd need to either wash and reuse clothing despite the water and energy costs, or accept wearing dirty clothes for extended periods. Neither option is pleasant. Personal space becomes another precious commodity. Your habitat will be small and you'll be sharing it with several other people constantly. You'll hear them all the time: conversations, snoring, bathroom sounds, everything. You'll smell them. You'll be aware of their presence constantly. The human need for solitude, for time alone to process thoughts and emotions, will be nearly impossible to fulfill. Some habitat designs include small private crew quarters, essentially closet-sized spaces where you can close a door and be alone, but even those don't provide true isolation from the sounds and awareness of others nearby. Conflicts are inevitable in such close quarters. Research from Antarctic stations, submarines, and space missions shows that interpersonal conflicts follow predictable patterns. Early in the mission, people are polite and accommodating. As time passes and stress accumulates, small irritations become major annoyances. Someone's habit of humming becomes intolerable. Another person's way of eating drives you crazy. Disagreements about task assignments or habitat temperature become heated arguments. The Sphinx 99 study, a simulation of long-duration spaceflight, witnessed this firsthand. A New Year's Eve celebration turned violent when two crew members got into a fistfight. Another crew member was forcibly kissed twice by a commander, creating a hostile environment. These weren't poorly selected individuals. They were trained professionals who had passed psychological screening. The environment itself creates stress that can overwhelm even the best training and intentions. On Mars, if relationships break down completely, there's nowhere to go. You can't request a transfer. You can't take a weekend off to visit other friends. You're stuck with these people, and they're stuck with you for the entire year. The crew must find ways to resolve conflicts, forgive each other, and move forward, because the alternative is mission failure and possibly death. Communication protocols become essential. Successful, isolated missions establish clear rules about decision-making, conflict resolution, and interpersonal behavior. Regular crew meetings provide structured opportunities to address issues before they explode. Scheduled private time with mission psychologists on Earth, despite the communication delays, offers a pressure release valve. But all of these interventions require energy and emotional labor when you're already exhausted and stressed. Let's shift to something that might surprise you: the challenge of scientific research. You might think that being on Mars would make scientific research easy, since you're right there on the surface. In reality, conducting meaningful science while also trying to survive is extraordinarily difficult. Every EVA to collect samples or deploy equipment requires hours of preparation, exposes you to radiation, uses up consumables from your spacesuit, and carries risks of injury or equipment failure. The spacesuits themselves are major obstacles. Current spacesuit designs are bulky, restrictive, and tiring to work in. The gloves, necessary to maintain pressure and protect your hands, make fine motor control difficult. Imagine trying to pick up small rock samples, operate delicate equipment, or perform repairs while wearing thick, pressurized gloves. Tasks that would take minutes on Earth stretch into hours. Your hands and arms become exhausted from fighting against the suit's internal pressure with every movement. Spacesuits can only sustain you for a limited time, perhaps 6 to 8 hours depending on the design. This includes the time to depressurize the airlock, exit the habitat, perform your work, return, and repressurize. The actual time available for productive work might be only 3 to 4 hours. Then you need to recharge the suit's life support, refill oxygen and water, recharge batteries, and perform maintenance checks. You can't just do multiple EVAs back-to-back whenever you want. The Martian environment also damages equipment in ways that are difficult to anticipate. The fine, abrasive dust gets into everything. It's electrostatically charged, so it clings to surfaces and is almost impossible to remove completely. The dust particles are sharp and angular because Mars lacks the wind and water erosion that rounds particles on Earth. This dust scratches visors, damages seals, clogs mechanisms, and degrades solar panels. Every time you return from an EVA, you bring dust into the airlock, and over time, it accumulates and causes problems throughout the habitat. Temperature extremes stress equipment constantly. Metal components expand and contract with the dramatic temperature swings between day and night. Seals become brittle in the cold. Lubricants behave unpredictably. Electronics can malfunction. Equipment that worked perfectly during testing on Earth might fail on Mars in ways that are difficult to predict or fix. And speaking of fixing things, let's talk about maintenance and repair, which will consume a substantial portion of your time and mental energy. Everything mechanical eventually breaks. On Earth, when something breaks, you order a replacement part or call a technician. On Mars, you are the technician, and you have only the spare parts you brought with you or can improvise from other equipment. The habitat systems, life support equipment, rovers, spacesuits, scientific instruments, communications gear, and power generation all require regular maintenance. Filters need replacing, pumps need servicing, software needs updating, and structural integrity needs monitoring. A failure in any critical system could be catastrophic, so preventive maintenance becomes an obsessive priority. But you have limited spare parts, and resupply from Earth is either impossible or extremely delayed and expensive. You'll need to become expert at improvisation, using duct tape, 3D printing, and creative problem-solving to keep things running. The movie The Martian depicted this realistically. Mark Watney survived by being a brilliant improviser who could solve one problem after another using limited resources. The difference is that you'll be doing this not in a Hollywood script where everything works out, but in reality where sometimes your improvised solution fails and you have to try again while your margin for error shrinks. The stress of constant problem solving under life or death pressure is exhausting in a way that's hard to convey. Every day brings new challenges. A seal develops a slow leak, a computer glitches, a battery doesn't charge properly. Individually, these are manageable problems. Collectively, they create a grinding mental burden where you can never fully relax because the next problem is always just around the corner. Documentation becomes crucial but tedious. Everything you do needs to be documented for mission control, for future missions, and for troubleshooting. When something goes wrong, engineers on Earth will need detailed information to help you fix it. This means constant logging of activities, equipment status, environmental readings and observations. It's necessary but time-consuming, and it adds to the feeling that you're not just living your life but performing it for an audience. Let's talk about something that combines physical and psychological challenges: the view. On one hand, you're seeing sights no human has ever witnessed in person. The Martian landscape has its own stark beauty: towering volcanoes like Olympus Mons, the vast canyon system of Valles Marineris, ancient riverbeds that tell stories of Mars's watery past, and alien rock formations shaped by billions of years of wind erosion. The sunsets are spectacular, tinted blue by the way dust scatters light in the thin atmosphere. The night sky is magnificent, showing stars without the light pollution of Earth, and from Mars you can see Earth itself as a bright blue-white star. But here's the psychological paradox: that same unchanging alien landscape becomes oppressive. The initial wonder wears off and you're left looking at the same dead, sterile world day after day. Nothing grows, nothing moves except wind-blown dust. Nothing changes except the slow cycle of day and night. The landscape that was initially fascinating becomes a constant reminder that you're on a dead world, utterly hostile to life, where every moment outside your thin, protective shell would kill you instantly. Earth, visible as a bright point of light in the Martian sky, becomes a source of profound longing. That tiny dot contains everyone you love, every place you've ever been, every experience of comfort and safety you've ever known. 7 billion people are living their lives there, breathing freely, feeling rain, seeing green plants while you're trapped on this rust-colored rock. The psychological term for this is Earth out of view phenomenon, though on Mars, Earth is technically in view, just impossibly far away. Homesickness on Mars would be qualitatively different from any homesickness experienced on Earth. When you're away from home on Earth, you know you could theoretically go back if you absolutely had to. There are planes, trains, and roads connecting you to home. On Mars, there's nothing connecting you to Earth except radio signals. The physical separation is absolute. You cannot go home. You cannot even begin the journey home until the launch window opens many months later. You're committed to staying no matter how much you want to leave. The knowledge that emergencies on Earth, family crises, deaths of loved ones, are happening without you, and that you can do nothing, not even attend a funeral or comfort someone in person, creates a unique form of grief and helplessness. You're simultaneously the most famous person in history, living humanity's greatest adventure, and utterly powerless to participate in the lives of the people you care about most. Now let's discuss something that mission planners worry about constantly: the what-if scenarios. What if the landing site turns out to have unexpected hazards? What if a critical component fails that you can't repair? What if someone becomes seriously ill or injured? What if a solar storm more powerful than predicted strikes? What if a micrometeorite punctures the habitat? What if political or economic changes on Earth lead to mission support being reduced or cut off? These aren't idle fears. Space exploration history is filled with missions that failed despite meticulous planning. Apollo 13 survived through a combination of brilliant engineering, improvisation, and luck. The Challenger and Columbia disasters demonstrated that even with NASA's expertise, things can go catastrophically wrong. The difference is that those were relatively short missions near Earth. On Mars, you're on your own for a year, and rescue is impossible. The psychological burden of living with these risks every day is immense. On Earth, you face risks constantly, crossing streets, driving cars, eating food that could theoretically be contaminated, but you've normalized these risks to the point where you don't consciously think about them. On Mars, you can't normalize the risks because they're constantly visible. You see the thin habitat wall separating you from instant death. You see the radiation dosimeter climbing. You feel the effects of reduced gravity weakening your bones. The danger is always present and undeniable. This creates a state of chronic hypervigilance, where part of your mind is always monitoring for threats, always listening for unusual sounds in the equipment, always watching for warning signs. This state of constant alertness is exhausting. It's similar to what soldiers experience in combat zones, and it can lead to anxiety disorders, sleep problems, and eventual psychological breakdown if it continues too long without relief. Sleep itself becomes problematic for multiple reasons. The Martian day, called a sol, is about 24 hours and 39 minutes long. This might not sound like much of a difference, but your circadian rhythm, your internal biological clock, is tuned to Earth's 24-hour day through millions of years of evolution. Some people can adapt to the slightly longer Martian day relatively easily. Others experience chronic sleep disruption, constantly feeling jet-lagged, never quite synchronized with the local day-night cycle. The lighting conditions complicate this further. If you're relying on natural light, the Martian day provides cues, but the quality of light is different from Earth, and during dust storms it can become dim and reddish, even during the day, disrupting your circadian signals. If you're in a habitat with primarily artificial lighting, You lose natural day-night cues entirely unless the lighting is carefully managed to simulate them. Sleep quality suffers in other ways too. The constant background noise of life support systems creates a drone that some people find impossible to sleep through. The stress and anxiety about survival make it hard to relax. The lack of physical exertion in reduced gravity means you might not feel physically tired even when mentally exhausted. Some astronauts on the ISS report sleeping poorly despite being constantly tired, and you'd likely experience the same. Sleep medication is an option, but comes with its own risks. In an environment where you might need to respond to an emergency at any moment, being heavily sedated is dangerous. Medications can also interact with other drugs you might need, cause side effects in the unusual physiological conditions of Mars, or create dependency issues. The medical officer would need to carefully balance the benefits of medicated sleep against the risks. Dreams become strange and sometimes disturbing in extreme environments. Antarctic researchers and astronauts report vivid, unusual dreams, sometimes featuring themes of confinement, danger, or Earth. These dreams can affect your mood and psychological state when you wake. Nightmares about habitat failures, being stranded, or disasters affecting Earth would be common and psychologically draining. Let's talk about something that's rarely discussed in the exciting promotional materials about Mars missions. Boredom. Yes, boredom. You might think that being on Mars would be constantly exciting, but the reality is that much of your time would be spent on routine maintenance, exercise, meal preparation, and waiting. Waiting for equipment to complete its cycle, waiting for experiments to run, waiting for communication windows with Earth, waiting for the right conditions for an EVA, waiting for something to go wrong so you can fix it. The crew would have entertainment options, books, movies, music, games, all stored digitally. But the library would be finite and quickly become familiar. You'd watch the same movies multiple times, read the same books again and again. New content would arrive with data transmissions from Earth, but always delayed, never quite current. You'd experience Earth's culture on a lag, always slightly out of sync, never able to participate in the immediate shared experiences that bind Earth's population together. Hobbies become crucial for psychological health, but are limited by the constraints of the environment. You can't go for a hike, you can't play most sports, you can't work with wood or do most crafts. Activities that require special materials or equipment beyond what was packed for the mission are impossible. Some astronauts paint, write, take photographs, play musical instruments, or exercise creatively, but the options are constrained. The lack of novelty slowly erodes mental stimulation. Human brains crave new experiences, new inputs, new challenges. In the monotonous Martian environment with the same people, the same food, the same tasks, the same views, your brain becomes understimulated. This can lead to cognitive sluggishness, difficulty concentrating, and depression. You might find yourself forgetting words, making simple mistakes, or feeling like your mind is becoming duller. Some researchers describe this as the third quarter phenomenon, where performance and morale drop significantly around the three-quarter point of a long-duration mission. The initial excitement has worn off, the end still seems far away, and the accumulated stress and monotony reach a critical point. For a one-year Mars surface mission, this would hit around month 9, just when you're beginning the final preparations for the journey home. Managing this psychological low point could make the difference between mission success and failure. Now let's address something that might seem minor but becomes significant: the loss of autonomy and privacy. On Earth, you make countless small decisions every day about what to eat, what to wear, where to go, who to see, how to spend your time. Most of these choices are made unconsciously and contribute to your sense of being an autonomous individual. On Mars, most of these choices are taken away. Your daily schedule is planned by mission control. Your meals are pre-selected based on nutritional requirements and available supplies. Your clothing options are limited to what was packed. You can't decide to take a day off and go to the beach. You can't spontaneously visit a friend. You can't change your hairstyle without considering how it affects helmet fit. You can't buy something on a whim. Every aspect of your life is controlled, monitored, and constrained by the mission requirements. This loss of autonomy is psychologically difficult for adults, especially for the type of highly educated, independent, competent people who would be selected for a Mars mission. These are individuals who are used to having control over their lives, making their own decisions, and being respected for their expertise. Being reduced to following schedules and protocols, having every decision scrutinized by mission control, and living under constant observation can feel infantilizing and frustrating. Privacy, as we understand it on Earth, essentially doesn't exist. Communications are monitored and recorded. Video cameras throughout the habitat track activities for safety and mission documentation. Your physiological data, vital signs, sleep patterns, exercise performance are all monitored and transmitted to Earth. Your psychological state is regularly assessed. Even in your small private quarters, you're aware that the walls are thin and others can hear you. The bathroom might be the only place where you have even the illusion of privacy. This constant surveillance, even though it's for legitimate safety and scientific reasons, creates psychological stress. Humans have a deep need for privacy, for spaces and times where we can be ourselves without observation or judgment. On Mars, you'd need to be on all the time, aware that your actions are being recorded and analyzed. Any moment of weakness, frustration, or breakdown becomes part of the permanent mission record and might be scrutinized by researchers, the public, or future historians. The pressure to maintain a positive public image adds another layer of stress. You're representing not just yourself, but your space agency, your country, and humanity as a whole. Billions of people are watching and judging. If you complain too much, you might be seen as ungrateful or weak. If you express doubts or fears, you might undermine public support for space exploration. If you have a conflict with a crew member, it becomes an international incident analyzed by media outlets. The psychological burden of this constant performance is exhausting. Let's talk about something that combines multiple challenges we've discussed: the return journey. After surviving a year on Mars, you'd face the prospect of the 7 to 9 month journey back to Earth. By this point, you'd be physically weakened by radiation exposure, bone density loss, muscle atrophy, and possibly other health issues that developed during the mission. You'd be psychologically exhausted from the year of isolation, stress, and sensory deprivation, and you'd have to face months more of cramped spacecraft living before reaching home. The spacecraft for the return journey would have been waiting in Mars orbit or on the surface for over a year, exposed to the harsh Martian environment. Systems would need to be checked, recharged, and verified before trusting your life to them for the journey home. The launch from Mars, while easier than launching from Earth due to lower gravity and no atmosphere to speak of, still carries risks. You'd need precise timing and execution to enter the correct trajectory back to Earth. During the return journey, you'd experience all the same problems as the outbound journey: microgravity health effects, radiation exposure, equipment failures, psychological stress, and the finite nature of consumables. But now you'd be dealing with these challenges while already weakened and exhausted. Your bone density is even lower, your immune system is even more compromised, your psychological resilience has been worn down by the year on Mars. The anticipation of returning to Earth would be both exhilarating and anxiety-inducing. You'd look forward to seeing loved ones, breathing fresh air, feeling rain, eating real food, and experiencing the sensory richness of Earth again. But you'd also worry: how much has changed while I was gone? Have my relationships survived? Will I be able to readjust to Earth's gravity and environment? What if something goes wrong with the landing? Earth return and landing present their own significant challenges. After 18 months to 2 years of reduced gravity exposure, your body would be severely deconditioned to Earth's gravity. The re-entry itself would subject you to several G-forces of deceleration, which would feel much more intense after so long in low gravity. Astronauts returning from just 6 months on the ISS describe re-entry as brutal and disorienting. After a Mars mission, it would be worse. Upon landing, you'd be unable to walk or even sit up without assistance initially. Your heart would struggle to pump blood against Earth's gravity, your muscles would be too weak to support your weight, your bones would be fragile and prone to fracture. You'd need weeks or months of physical rehabilitation just to regain basic mobility, and some effects, particularly the radiation damage and bone density loss, might be permanent. The psychological adjustment to Earth would be complex and potentially difficult. After nearly 2 years in small confined spaces with the same few people, the sensory richness of Earth, the crowds, the chaos, the constant stimulation, could be overwhelming. Psychologists call this reverse culture shock or re-entry syndrome. You'd have changed profoundly during the mission, while Earth and the people you knew continued evolving in their own directions. The disconnect between who you were when you left and who you've become, between the Earth you left and the one you've returned to, can create a profound sense of alienation. Some astronauts report feeling more comfortable in space than on Earth after long missions, feeling like they don't quite fit anymore in the world they came from. After a Mars mission, you might struggle with the feeling that nobody on Earth can truly understand what you experienced. You'd have gone through something so extreme and unique that it creates a permanent divide between you and almost everyone else on the planet. Only your crew members would truly understand, creating bonds that are both intensely strong and potentially isolating from everyone else. The media attention would be intense and inescapable. You'd be one of the most famous people on Earth, constantly requested for interviews, appearances, and speaking engagements. While some of this attention might be gratifying, it would also be exhausting when you're trying to physically recover and psychologically readjust. The public would have expectations about how you should behave, what you should say, and how you should feel about the experience. Living up to these expectations while dealing with your own complex and possibly conflicting emotions would be challenging. There's also the question of what comes next in your life. You've accomplished something that only a handful of humans in history have done. You've stood on another planet. Where do you go from there? What challenge could possibly match that experience? Some astronauts struggle with finding purpose and meaning after their spaceflights, feeling like everything else is anticlimactic. After a Mars mission, this feeling could be particularly acute. Physical health monitoring would continue for the rest of your life. You'd be a unique medical subject, one of the first humans to experience long-duration interplanetary travel and Martian surface living. Your cancer risk would be elevated due to radiation exposure. Your bone density and cardiovascular health would need ongoing monitoring. Any unusual health issues you develop would be analyzed to determine if they're mission-related. In a sense, you'd never be fully free of the mission. It would mark your body and your medical records permanently. Let's step back and consider the bigger picture. Why would anyone agree to this? Given everything we've discussed, the physical suffering, the psychological stress, the risks, the permanent health effects, why would someone volunteer for a Mars mission? The motivations would be complex and varied. Some would be driven by the pioneering spirit, the same impulse that drove explorers throughout human history to venture into unknown territories despite the dangers. The desire to be first, to see what no human has seen, to push the boundaries of human achievement is a powerful motivator for certain personalities. Others would be motivated by a sense of contributing to something larger than themselves, advancing human knowledge and capability, potentially ensuring the long-term survival of our species by making us multi-planetary. The narrative that Mars colonization is essential for humanity's future is compelling to people who think in civilizational timescales and want their lives to have lasting meaning beyond their own existence. Scientific curiosity would drive some volunteers. The opportunity to conduct research on Mars, to study its geology, search for evidence of past life, and understand planetary evolution in ways that are impossible from Earth would be irresistible to certain scientists. For them, the physical and psychological costs might seem worth it for the chance to answer fundamental questions about our solar system and the nature of life itself. Some people would be motivated by personal circumstances, a desire to escape from a difficult situation on Earth, a lack of close family ties that would make the separation less painful, or even a terminal illness that makes the long-term health risks less relevant. While space agencies screen carefully to avoid selecting people who are running away from problems rather than running toward a goal, the reality is that personal circumstances influence everyone's decision-making. The selection process itself would be extraordinarily rigorous, probably more so than any selection process that's ever existed. Physical health requirements would be strict: excellent cardiovascular condition, no genetic predispositions to radiation-sensitive cancers, optimal bone density, perfect vision or reliably correctable vision, no chronic conditions requiring ongoing medication, and robust immune function. The candidate pool would immediately be limited to a tiny fraction of humanity. Psychological screening would be equally demanding. Evaluators would look for emotional stability, stress tolerance, ability to function in confined spaces, compatibility with isolation, strong interpersonal skills, conflict resolution abilities, adaptability, problem-solving skills, and the capacity to maintain morale during extended hardship. They'd also screen out anyone with tendencies toward depression, anxiety disorders, claustrophobia, or other conditions that could be catastrophic in the Mars environment. Technical skills would be essential. Every crew member would need to be multi-talented, perhaps a geologist who's also trained in emergency medicine, an engineer who can also operate scientific equipment, a physician who's also a skilled pilot. The crew would need to be collectively capable of handling virtually any problem that might arise, from medical emergencies to equipment repairs to scientific research to emergency spacecraft operations. Even after selection, training would take years. Candidates would spend time in analog environments, Antarctic stations, underwater habitats, desert isolation facilities, and other locations that simulate some aspects of Mars living. They'd train extensively in spacecraft operations, EVA procedures, habitat maintenance, emergency protocols, scientific procedures, and interpersonal dynamics. They'd be evaluated constantly, and many would wash out during training when it becomes clear they can't handle specific aspects of the mission. The families of Mars mission crew members would face their own challenges. They'd spend years knowing their loved one is in constant danger, unable to help if something goes wrong, dealing with communication delays that make real conversation impossible, and watching the person they love become physically weakened and changed by the mission. Children would grow up significantly during the mission, possibly reaching developmental milestones without their parent present. Relationships would be tested in ways that most couples never face. Despite all of these challenges, when space agencies eventually announce crew selection for the first crewed Mars mission, they'll likely receive tens of thousands of applications. This says something profound about human nature. We're drawn to exploration and challenge, even when the rational calculation of risks and rewards suggests we shouldn't be. The same impulse that drove ancient humans to cross oceans in small boats, to climb mountains, and to venture into unknown territories continues to drive us toward the planets. But it's crucial that we go into this with clear eyes, understanding the real costs and challenges, not the sanitized, romanticized version often presented in marketing materials and popular media. The people who volunteer for Mars missions deserve to know what they're really signing up for. The public that will fund these missions deserves to understand what we're asking these astronauts to endure on our behalf. Mars colonization, if it happens, will be built on the suffering and sacrifice of the first generations of Mars explorers. They'll pay with their health, their psychological well-being, possibly their lives, to establish the knowledge and infrastructure that might someday allow Mars settlements to become sustainable. They'll be heroes, but they'll also be, in a very real sense, martyrs to the cause of human expansion into the solar system. The vision of thriving cities on Mars, of terraformed landscapes with breathable atmospheres and flowing water, of humanity spreading throughout the solar system, is inspiring and may even be achievable eventually. But the path from here to there runs through decades or centuries of hardship that will test the limits of human endurance and determination. The first people to attempt living on Mars will face challenges that make the most difficult feats in human history seem comfortable by comparison. Understanding these challenges doesn't mean we shouldn't attempt Mars exploration and eventual colonization. It means we should do so with respect for the magnitude of what we're attempting, with adequate preparation and support for the people we're sending, and with realistic expectations about the timeline and costs involved. The exploration of Mars will be one of humanity's greatest achievements, but it will be earned through immense effort, sacrifice, and suffering by the brave individuals who go first. So the next time you see an exciting video or article about Mars colonies and interplanetary civilization, remember what we've discussed here. Remember the radiation slowly damaging DNA, the bones weakening in low gravity, the psychological stress of isolation, the constant equipment failures, the unrelenting danger, and the physical and mental toll on the human beings who would make it possible. The reality of Mars is far more challenging and far more terrifying than most presentations suggest. If this deep dive into the harsh realities of Mars exploration has fascinated you, the video on the screen is a must-watch. Mars colonization is more terrifying than you think. See you there.